Take a look at this picture of the Ring Nebula in the constellation Lyra. You can see it's highlighted with many colors, and in the center is a white dwarf star. And as you look at this, it's pretty magnificent, but also there's a lot known about this, that this is the result of at some point of a supernova explosion. In other words, a large star exploded, and as the gases were expanding outward, the remnant of the star contracted inward to form this white dwarf, white star in the middle here, and these other gases continue to expand outward. The point in showing this beautiful Ring Nebula is that how do we know these things? How do we know anything about astronomy? How do we know what we know? We know what we know about the universe because we can gather information from the light that comes to us. So we can get different information from the different kinds of light that comes to us. Here's another example. Here's the Andromeda Galaxy, 2.9 million light years away. It is the nearest galaxy to our own Milky Way, and it is moving toward us. At some point in the distant future, the two galaxies will collide and form a mega galaxy. Question is, how do we know that? How do we know that the Andromeda Galaxy is 2.9 million light years away? In other words, it takes light 2.9 million years to get to us. So this is an image that is 2.9 million years old. And how do we know that this galaxy is moving toward us as opposed to away from us? How do we know these things? We gather all this information from light. Here's a picture of the first extrasolar planet ever having a picture made of it. In other words, extrasolar meaning outside of our own solar system. And this planet is 25 times heftier than Jupiter. It is 55 astronomical units away from its brown dwarf star. And in particular, this planet contains, its emission of its light contains water. So how do we know that? How do we know that how far the star is, this planet is away from its own star? How do we know what exists on this planet? How do we know that there's water there? And again, the answer is from the different aspects in the study of light and different ways to study light. So all this information that we have in astronomy basically is coming from the way that we analyze light. Well, so we need to know something about light so that we can discern this information. And one thing that light is, it's a wave. And you can get information from waves. Waves are produced by disturbing matter. If you can disturb matter, it will produce a wave, and that information will be distributed. Waves transfer energy, not the matter themselves. So even though matter may move, when we're talking about waves, we're talking about the energy that is transported through matter, from matter to matter. In particular, mechanical waves require a medium. For instance, when you look at ripples in water, that is an energy that's been transported from one locality in water to the next locality in water, and so forth and so on. And so the medium of the water is what helps transport that information, that wave. Sound. Sound needs a medium. In particular, the sound that we hear on Earth needs air to transport the energy. Air is a collection of molecules flying around, and so when you have sound, you have a pressure wave through that air. It causes a disturbance in the air, a condensation and rarefaction of the air at different points, where it creates a pressure difference in the air. That pressure difference travels through the air to your eardrum, and when it hits your eardrum, it moves your eardrum back and forth due to the pressure difference, and that movement of the eardrum is interpreted by your brain as sound. If there was no air, you would not be able to hear sound. Fields of grain, if you ever see a full field of grain, say of a wheat or something like that, and the wind comes along and hits some of the stalks on one side of the field and pushes them over so that they hit the neighboring stalks, and then they hit the neighboring stalks, so you have these stalks of grain hitting the adjacent stalks of grain, and so you can see this wave travel across this field of grain. But the medium itself, the stalks of grain, don't actually walk across that field. They are stuck to the ground. So they're only moving locally, while this energy of this wave is traveling through the medium across the field. Waves on a string. You can see waves on a string have a taut string, and you initiate a wave on one side, and you can watch that wave go down the string. But the string itself only moves up and down. It doesn't move from one place to the next. It's the wave that is moving across the string. Earthquake. You can have a disturbance, an energy of an earthquake at some point on the Earth's crust, and that energy will move through the ground. It will shake the ground, and the neighboring ground will be disturbed, and that energy gets transferred from ground to ground until finally it manifests itself somewhere on the surface. And what you don't have is you don't have the ground where the earthquake was actually moving itself to the ultimate destination. It is the energy that moves through the ground as a medium, finally getting to the ultimate destination, where locally things are moving due to the end result of that wave. The only kind of waves that we know that require no medium are electromagnetic waves, light. This has been verified by many experiments, and in fact, light can travel through a vacuum. It can travel through nothing. Here's a definition of a type of wave. A transverse wave is a type of wave where the medium will move in a transverse direction while the wave itself propagates in a forward direction. For instance, on this string, if we look at this, the hand is initiating a wave on the string, and the wave moves down the string. The string is actually moving locally up and down while the wave is progressing forward in a forward direction. So we have a transverse movement of the medium while the wave is moving forward in a linear direction. Another kind of wave would be a longitudinal wave, where the oscillation of the medium is actually along the same direction as the wave propagation. For instance, in this spring, if you initiate a spring wave, you can see the condensation of the spring progress down the spring as it's moving forward, and that movement back and forth of the spring is actually in the same direction as the movement of the wave itself. So that is a longitudinal wave. Water waves are combinations of both. A water wave has a transverse component and a longitudinal component, and the combined effect of both of those is a circular motion, an overtow and an undertow. For instance, in a water wave, let's say you had a earthquake off the coast of Peru, and initiated all this energy in this wave that travels across the Pacific. And what happens is the water is moving through an overtow and undertow effect, and the local variation in one point transfers the energy to the next point, which moves in a circular motion, and the next point in a circular motion. And this wave could travel across the Pacific Ocean, and there might even be a ship on the middle of the ocean, and the wave would just travel underneath the ship, depending on what its amplitude is. And the ship may never even know that wave has passed through. And it's traveling across the ocean, and it's doing this undertow, overtow effect until it finally gets to the continental shelf of, say, Japan. And it's doing this thing, and it's pulling in and pulls this water in, and then all of a sudden there's no more water. So on the overtow, you've got this tsunami who hits the shoreline of Japan, say. So the energy of the earthquake has been transferred across the Pacific through the medium of the water, but the water from Peru has not actually traveled from Peru to Japan. The actual water that hits Japan is the water that was there locally and was affected by this wave as it came in. So effectively, a wave transfers energy, and by doing so, it also transfers information. If we say if we were in a little pond and all of a sudden you felt a wave come towards you and hit you, you might discern some information from that. You might say, well, you know, I think something fell into the pond somewhere else. It fell into the pond, created this wave. This wave came to me, and now I know that something fell in the pond. And by the size of the wave, I can probably figure out how big that something was. So, in essence, I've received information through the transfer of this wave. Well, light pretty much works the same general way. Light is an electromagnetic wave is created by a movement of charge, and so if you have a vibrating charge, an accelerating charge would have to be the effect. It will send off an electromagnetic wave of a particular frequency and amplitude. That wave will travel, and at some distant point there might be another charge that will be affected by that wave. Because of this energy and this electromagnetic wave, it will move that charge up and down, and hence the receiving charge will have an action that is the result of the vibrating charge, the original vibrating charge. So you will receive a signal that is similar to what was sent out. So a moving charge creates a field wave. The receptor charge is affected, and hence information and energy is then effectively transferred. Light is an electromagnetic wave, and it's got wave properties. It has a wavelength. The wavelength is defined as the distance in which the wave repeats itself, at least spatially. So it could be from a peak to a peak, or it could be from any equivalent point on the wave to the next equivalent point. So the wavelength is the distance in which a wave repeats itself. The wave could also repeat itself in time. If you were to just focus on the wave at a particular moment or a particular point, and just watch it travel up and down, at some point it's going to repeat itself at that same point, and so over a certain amount of time it will take to repeat itself. We call that the period. 1 over the period is called the frequency. The frequency is the number of times per second that the wave will pass a point. So the frequency is 1 over the period. So as I'm watching this wave go by, as it goes up and down and passes that point, then the frequency would be how many times per second does it do that. we define what we call the velocity, at least for electromagnetic waves, by c. We probably use c because the velocity for light and electromagnetic waves is a constant. So c probably developed from the idea that it is indeed constants per second. So it gives you a kind of a distance per second units on that. And that is the speed of light, speed of electromagnetic waves. For the speed of light, that is 300,000 kilometers per second, or 186,000 miles per second. Or, since the Earth has a circumference of 25,000 miles, that is 7.5 times around the Earth per second. So light will travel every second, 1,001. The Moon is 250,000 miles away. So it would take approximately 1.5 seconds traveling at the speed of light to get to the Moon. So anytime people are trying to communicate with astronauts on the Moon, they have to pause a little bit. So they say something, and then there's 1,001 and a half second before they get a response, because it takes time for that signal to get there to the Moon. This constant speed of light is equal to the wavelength times the frequency. Since the speed is constant, that means if you change the wavelength, the frequency will change inversely. So if the wavelength were to go up, the frequency would go down, or if the frequency were to go up, the wavelength would go down, such that the product of the two will still remain constant. So the wavelength and frequency vary inversely. If the frequency were to double, then the wavelength would be halved. As you can see here at high frequency in the blue range here, we've got a lot happening per second, and the wavelength is shorter. So a shorter wavelength with high frequency, or a longer wavelength with low frequency. We're talking electromagnetic waves. So there's an electric component to this wave, and there's a magnetic component to this wave. So to understand it fully, we need to understand a little bit about magnetism, or at least the source of magnetism. For the Earth in particular, the Earth has a magnetic field, and the reason it has a magnetic field is because there is electronic material in the Earth's outer core that is swirling around due to the Earth's rotation. And so it's the movement of that electronic material that creates the Earth's magnetic field. In other words, a changing electric field, changing electric material creates a magnetic field. Well, light has both electric field and magnetic field components to it. And as the electric field is changing, it is in a sense creating the magnetic field, which is also changing, and equivalently creating the electric field. So they're both changing simultaneously and inducing the other. And they're doing this perpendicular to each other, at the same time traveling in a forward direction. So we have a electric field variation and a magnetic field variation happening perpendicular to each other as this wave is propagating forward. Changing one causes the other. Light can have a spectrum to it. If we're looking in particular at visible light, white light coming into, say, this prism, it travels at different speeds through a medium. It travels at the same speed through a vacuum, but through a medium, different frequencies of light will travel at different speeds because of the way that the medium absorbs the light, absorbs the different frequencies. And in particular, the speed of red waves will be faster than the speed of blue waves in that medium, because the frequency won't change, but the wavelength will change. So the longer red wavelengths are affected less than the shorter blue wavelengths, hence they are deflected less. The blue is deflected more, and hence you get the colors of the rainbow coming out of this prism, the whole spectrum, visible spectrum coming out of this prism. That's a continuous visible spectrum from red, orange, yellow, green, blue, and violet, Roy Gabiv. As we look at the different components of white light, visible white light, all that is just a very small fraction of the whole electromagnetic spectrum. So if you think about all the information you can get from light itself, in other words, you can get colors, you can get hues, you can get different shades, you can get perspective, you can get dimensions, you can see things and discern things just from visible light. But visible light, in terms of all light, is just a small little fraction of the whole spectrum of electromagnetic radiation. So we can get a lot of information from visible light, but we can get a lot more information from looking at all aspects of light, all electromagnetic radiation. In other words, if we consider radio waves, microwaves, infrared radiation, visible spectrum, ultraviolet, X-rays, gamma rays, we can get different information about the universe from all these different ranges of the electromagnetic spectrum, and it'll tell us different things. So we can get a whole source of information from all this light. If we try to observe that on the ground on the Earth, we are limited because our atmosphere protects us from much of that radiation that's coming into the Earth. And in particular, it protects us from almost all the radiation except for two particular windows through our atmosphere. One is the optical window, so we get the optical light, the visible light that's coming from the heavens. And there is a radio window that's coming through our atmosphere as well. So if we're trying to collect information while we're sitting here on Earth, the kinds of information we can collect is mainly optical and radio. Some infrared and just a little bit of ultraviolet. Our eyes are most sensitive to 550 nanometers, which is in the center of that optical window. So if I were a biologist, which I'm not, I would say that we are adapted to the most intense radiation that we receive, which would be the middle of the optical window, 550 nanometers wavelength. To see the rest of the spectrum, we need to get outside our atmosphere. So we need to put out satellites or some other telescopes beyond our atmosphere so we can collect this other information. Here's a radio radio telescope array in New Mexico. It's called the VLA, Very Large Array, and it does radio astronomy. So it's utilizing that big window for radio waves and doing astronomy here on Earth. Here are telescopes at the top of Mauna Kea in Hawaii, and they're doing visible astronomy. So they're utilizing that other window at a very high height, so the atmosphere is thinner there and clearer there, and hence getting better results for optical measurements. Like we said, if we want to see everything, we want to get outside the atmosphere. So we put up something like the Hubble telescope, which can see all the wavelengths and frequencies of light. So the outer regions of the electromagnetic spectrum can be detected by the Hubble. It's a good example of an instrument outside Earth's atmosphere which can collect infrared, microwaves, ultraviolet, and so forth, X-rays and so forth. For instance, here's a picture of a very famous object in the universe just by radio waves. It's radio waves that have made this image that's been enhanced to look optical to us so that we can see a picture of it, but it's created by radio waves. Here's the same object through infrared, IR. And we can see it looks somewhat different, and we may even notice an object in the middle of it, which looks like it might be another white dwarf in the middle of this object, looking at it just purely from infrared. Here's the object as it looks visibly through colors of the visible spectrum. And here's how it looks through X-rays. Totally different. Focused on that part of the electromagnetic spectrum. The Hubble can combine all these and try to make it look like a picture to us optically. And here's the composite picture of this object. A very famous object in the sky. Do you know what this is? I'll give you a little bit of history on it. In the year 1054, there was a supernova explosion. It was so bright that it lit up the sky for about a month. The Chinese astronomers said that basically it was almost like daytime for about a month during the night. And when that supernova died down, what was left was this remnant. And have you guessed what it is? Well, recently the Hubble's been updated to higher resolution, so I can show you the latest, highest resolution of this object, and it looks like this. It is the Crab Nebula, and this is the highest. Okay, all right. So this really is not the highest resolution of the object. This is just me playing a joke on you. But this is indeed the Crab Nebula, which is the result of that supernova explosion back in 1054. Some more information that we can gather from the universe is temperature. We can get temperature from light. And in order to harness this information best, we need a good temperature scale to do this. Now, we're all familiar with the Fahrenheit scale and the Celsius scale, but the Kelvin scale is a little bit less known. These are three different temperature scales that could be used. The Fahrenheit scale is defined in the middle by the properties of water. We know that water freezes at 32 degrees Fahrenheit, and it boils at 212 degrees Fahrenheit. So there's 180 degrees difference in the properties of water, water being a very important compound as we know it because we're 95% water ourselves. So water is something we wish to focus on. Well, if we do focus on those properties of water, where it freezes and where it boils, we can create ourselves another scale, the Celsius scale, and just define it in such a way that 0 is where water freezes and 100 is where water boils. So we have a 100-degree scale that defines those phase differences of water, and instead of 180, we now have 100. So for every 9/5 of, or almost 2 degrees temperature on a Fahrenheit scale, we have 1 degree on the Celsius scale. Now, using the scale, though, then colder temperatures than freezing on water would take us down to minus 273 degrees to the absolute coldness that we can go. And the problem for science is that if you have a temperature scale that goes negative, it causes problems for your equations, because you may have some equations that depend on the temperature to a even power, and if you put a negative number and either square it or go to the 4th power or even power, you're going to come up with a positive number, and it's just going to goof up all your calculations. So to account for that, the Kelvin scale has the same degree measurement as the Celsius scale. In other words, it's got the same unit of degrees, where there's 100 degrees between freezing and boiling for water. However, it redefines the lowest possible temperature as being 0. So absolute 0, where it's the coldest possible temperature, is indeed 0 on the Kelvin scale, and all temperatures above that are positive. And with this scale, it's much better for use in science. So that is the scale that is generally used, the Kelvin scale. So we have good, better, best. Using this scale, if we were to plot intensities of objects, in particular stars, we could plot intensity as a function of frequency, and we would get a skewed curve that looks something like this. It turns out that the peak of that curve, black bodies are perfect absorbers and radiators. The objects are not necessarily black, and most likely they are indeed white, at least as they appear to us, because stars are black bodies. The curve has a distinctive intensity peak corresponding to a particular temperature. So as this peak moves to a higher frequency, that would be a higher temperature. As this peak moves to a lower frequency, that would be a lower temperature. This temperature relationship between the peak of the blackbody curve and the temperature of the object that we're looking at is called Wien's law, and it looks like this. The maximum wavelength is equal to 0.29 centimeters divided by the temperature of the object. And this has kind of been verified through much data, but this gives us an idea for determining the temperature of the object, because we can get the maximum wavelength and discern the temperature from that. The wavelength will be halved if the temperature is doubled. Also, since wavelength and frequency are inversely proportional, the hotter the star, the higher its frequency, and the bluer its color. So stars that get bluer and even get up into the ultraviolet or X-ray part of the spectrum are very, very hot stars. Related to this is the Stefan-Boltzmann Law, which states that the intensity that we receive of light is proportional to the temperature of the object to the fourth power. So if you use the Wien's law to figure out the temperature of an object, you can get an idea of the brightness of the star, and its absolute brightness of the star, of its intensity, by associating that with the temperature of the fourth power. So we can get a knowledge of how really bright that star actually is on an absolute scale by its temperature. Intensity is power per area. Power is energy per time. So energy is related to the fourth power of the temperature. So we can see how luminous that star is. Because this is more than just looking at it and seeing how luminous it is, because when we look at a star, we really don't know how far away it is. So this would really tell us how luminous it is on a absolute scale. Here are some blackbody curves for some objects in the sky. And this first curve has a peak temperature of 60 Kelvin, and no part of its spectrum actually is in the visible spectrum. So if you were to look out in the sky in the direction of this object, you would not be able to see it. You'd have to take in this electromagnetic spectrum in the infrared and figure out its temperature based on that. So this would be an object that you would not be able to see. The second object is a red dwarf, and we can see that just part of its spectrum just barely makes it in the visible. So it would appear red to us. Its actual temperature is 600 Kelvin, so it's below the visible range, and hence this would be something that would be very difficult to see. Probably you could see it with some instruments, so you could see the red part of that spectrum. Here's a blackbody curve of our sun, and we can see it peaks right in the visible spectrum. So, like I said, if you were a biology instructor, you would say that we have adapted our eyes. We see the visible spectrum because that is the major portion of light that we receive. and hence that's where the sun peaks. The sun's surface temperature is 6,000 Kelvin, and that's how we know that its surface temperature is at the temperature. This last picture is a picture of a very bright cluster of stars, and if you were to look at it, you probably would appear blue to you, because what you would see is the higher intensity that would be at the upper fringe of the visible range, but really the actual peak would occur in the ultraviolet. So the greatest amount of intensity of light would be light you couldn't see in the ultraviolet range, and that would tell you, that peak would tell you what the temperature of that object was. To do a blackbody curve like these, you really only need 2 points. If it's a blackbody curve, 2 points would determine the whole curve. And so this kind of work with light could be very fruitful just by using 2 filters and measuring 2 points and then coming up with the curve. That concludes this first lecture on light. It kind of focused on the wave aspects of light. In the second lecture, we will look at spectroscopy and focus on some of the particle aspects of light.